Section 5.4 is about the greatest common factor and the least common multiple. So these are the only two objectives here: to find the greatest common factor by several methods, and then also to find the least common multiple by several methods. So here's the definition of the greatest common factor. So the GCF, or greatest common factor of a group of natural numbers, is the largest natural number that is a factor of all the numbers in the group. So for example, 18 is the GCF of 36 and 54 because 18 is the largest natural number that divides both 36 and 54. And then another example would be 1 is the GCF for 7 and 16. There are no other factors that are common to 7 and 16. And just for your information, the GCF, the greatest common factor, is often called the greatest common divisor as well. So there's different methods of finding the greatest common factor, and the first one is to use the prime factor method. And so step number 1 is to write the prime factorization of each number, and then choose all primes common to all factorizations, with each prime raised to the least exponent that it has in any factorization. And then the last step is to form the product of all the numbers in step 2. And this product is the greatest common factor. Especially step 2 might be a little bit hard to understand just when you read it, but we will do some examples of it, and then it should become clear how this is done. So we'll be doing 4 exercises. So when we look at number 11, 84 has a prime factorization of 2 to the second power times 3 times 7, and 140, its prime factorization is 2 to the second power times 5 times 7. Following step, so that's step number 1. Step number 2 is we choose all primes common to all factorizations, with each prime raised to the least exponent that it has in any factorizations. So we have 2 squared is common to both, and 7 is common to both expressions also. So in other words, following step 3 then, we form the product of all numbers in step 2. So then the product would be 2 squared times so go again, 84, the prime factorization is 2 squared times 3 times 7, and 140 is the prime factorization is 2 squared times 5 times 7. So we notice that 2 squared and 7 are common to both numbers. So 2 squared times 7 is 7 times or 4 times 7, or 28. So 28 is the greatest common factor for 84 and 140. So 28. For number 12, the prime factorization of 225 is 3 squared, 3 to the second times 5 to the second. And the prime factorization of 150 is equal to 2 times 3 times 5 squared. So 5 squared, or 5 is a common factor, and 3 is a common factor, 5 squared. And the least exponent for 3, which is common to both, would be 3. So then the greatest common factor would be 3 times 5 squared, or 3 times 25, or 75. That would be the greatest common factor. The prime factorization of 275 is equal to 5 to the second power times 11, and the prime factorization of 132 is equal to 2 to the second power times 3 times 11. So the only common factors would be 11, and so that is also the greatest common factor here, 11. Since 5 and 2 and 3 are not common to both numbers. In number 14, the prime factorization of 252 is equal to 2 to the second power times 3 to the second power times 7. And the prime factorization of 396 is 2 to the second power times 3 to the second power times 11. So we find that 2 to the second power and 3 to the second power are common to both, and those are also the least exponents. So in other words, the greatest common factor would be 2 to the second power times 3 to the second power, or 4 times 9, or 36. So 36 is the greatest common factor of these two numbers, 252 and 396. So let's look at number 19. So we write 600 and 90 next to each other. And so we notice that 5 is a prime factor, and dividing 600 by 5 gives us 120 and 18. Now we notice that 3 is a prime factor of 120 and 18, so we divide 3 into 120 by 3, and that's equal to 40, and 18 divided by 3 is 6. And now we have another prime factor of 2 that we can divide in 40 and 6, so we get 20, and we get 3, but there's no more common prime factor for 20 and 3, so therefore the greatest common factor would be 5 times 2 times 3. So we divide 690 by the prime factor of 5. That gives us 120 and 18. We divide 120 and 18 by 3. That would be prime factor. So we get 40 and 6. And now we have a prime factor of 2. We can divide into 40 and 6. And so it'll be 20 and 3. And there are no more common prime factors for these two numbers. So then the greatest common factor, the GCF, would be 5 times 2 times 3, or 30. So that's the greatest common factor for 690. Similarly, for number 20, we write the numbers next to each other, 237 and 395. So when you experiment a little bit with the numbers, you find out that 79 is a prime factor for 237 and 395. So when we divide 79 is 237, we get a 3. And when we divide 79 into 395, we get a 5. And so there are no more common factors for 3 and 5. So that would be the greatest common factor then, 79. For number 21, we're writing next to each other 84, 90, 210, and we see that 2 is a common prime factor, so we divide 84 by 2, we get 42. And 90 divided by 2 is 45, and 210 divided by 2 is 105. So now we see that 3 is a common prime factor, and so 42 divided by 3 is 14. 45 divided by 3 is 15, and 105 divided by 3 is 35. And there are no more common factors, prime factors for 14, 15, and 35. So therefore, the greatest common factor is 2 times 3. 2 times 3, or 6. So 6 is the greatest common factor for these three numbers. Similarly, for number 22, we have 585, 1,680, and 990. Okay, so the greatest common prime factor would be 5. And when we divide 585 by 5, we get 117. And 1,680 divided by 5 is 336. And 990 divided by 5 is equal to 198. And we realize that each number can be divided by 3, so 3 would be another common prime factor. So 117 divided by 3 is 39. And 336 divided by 3 is 112. And 198 divided by 3 is 66. And so now, since 39 is 3 times 13, and neither 3 nor 13 is a factor of any of these numbers, well, 3 is a factor of 66. So that would be all. So the greatest common factor in this case is equal to 5 times the product of 5 times 3, which is 15. So that's the greatest common factor for these given three numbers: 585, 1,680, and 990. Next, we're going to talk about the Euclidean algorithm, which is helpful if the two numbers are difficult to factor into primes. And so the algorithm is summarized here for finding the greatest common factor using the Euclidean algorithm. So to find the greatest common factor of two unequal numbers, divide the larger number by the smaller number. Note the remainder and divide the previous divisor by the remainder, and continue the process until a remainder of 0 is obtained. The greatest common factor is the last positive remainder obtained. Let's do some examples. So following the directions, we divide 18 into 64. So 18 divided into 64 is equal to 3, and 3 times 18 is into 60 rather. And 3 times 18 is 54. So the remainder is 6. And now we divide the previous remainder, 18, the divisor divided by 6. That's equal to 3. And 3 times 6 is 18. So now the remainder is 0, which means that 6 is the greatest common factor for these two numbers, So again, we divide 18 into 60, so that's 3 times 18 is 54, remainder of 6. Now we use the divisor of 18 here and divide 6 into that. And so 6 into 18 is 3 times. 3 times 6 is 18. So we subtract the remainder 0. So in other words, this would be the greatest common factor, 6. So for number 24, we divide 77 into 84, so 77 divided into 84 is 1, and 1 times 77 is 77. We subtract. So the remainder is 7, so we use this 77 now, 77, divided by the remainder of 7, and that's equal to 11, and 11 times 7 is 77. We subtract, and the remainder is 0. Therefore, 7 is the greatest common factor of these two numbers. For number 25, we divide 36 into 90. So 36 divided into 90 is equal to 2, and 2 times 36 is 72. We subtract, so the remainder is 18. So we take our 36 divided by 18 by the remainder. That's equal to 2. 2 times 18 is 36. We subtract, and the remainder is 0. So therefore, 18 is our greatest common factor here. 18. And for number 26, we divide 72 into 96. 72 divided into 96 would be 1. 1 times 72 is 72. We subtract. So the remainder is 24. So now we use our divisor of 72, and divide it by 24. And that would be 3 times, and 3 times 24 is 72. We subtract, the remainder is 0. Therefore, 24 is the greatest common factor. For these two numbers, 72 and 96. So you have learned 3 methods for computing the greatest common factor. One would be the prime factors method. The other one would be the greatest dividing the prime factor method, and then dividing, using the Euclidean algorithm. So 3 ways to get the greatest common factor for a group of numbers. Another important concept in number theory is that of the least common multiple, and so it's closely related to the idea of a greatest common factor. And the least common multiple is defined as follows. The least common multiple, or the LCM, of a group of natural numbers is a natural number, is the least natural number that is a multiple of all the numbers in the group. For example, 30 is the LCM of 15 and 10, because 30 is the least number that appears in both sets of multiples. For example, multiples of 15 are 15, 30, 45, etc. Multiples of 10 are 10, 20, 30, and so 30 would be the least common multiple. That's the first one that shows up here. And again, there are several ways to find the LCM, the least common multiple, and one of them is the prime factors method. So we begin again by writing the prime factorization of each number. Then we choose all primes belonging to any factorization, with each prime raised to the power indicated by the greatest exponent that it has in any factorization. And then form the product of all the numbers in step 2. And this product is the least common multiple. So here we have some exercises. Number 31 for the two numbers 81 and 45 to find the least common multiple. So we write down the prime factorizations. So for 81, the prime factorization is 3 to the 4th power. And the prime factorization of 45 is 5 times 3 to the 2nd power. So we use the largest exponent, the greatest exponent, so 3 to the 4th. And so 5 has only one exponent here, 5 to the 1st power. So then the least common multiple is equal to 3 to the 4th times 5, and that is equal to 405. So that is the least common multiple. In other words, at the smallest number into which we can divide both 81 and 45. For 84, over number 32, 84, the prime factorization is equal to 2 squared times 3 times 7, and the prime factorization of 70 is equal to 2 times 5 times 7. So we use, for the least common multiple, the LCM. We use, for 2, we use 2 squared times 3 times 5 times 7. And so it'd be 35 times 3 is 105 times 4 is 420. So then the least common multiple for these two numbers is 420. Again, that's the smallest number into which we can divide both 84 and 70. For number 33, we have the numbers 20, and the prime factorization of 20 is equal to 2 to the second power times 5. For 30, the prime factorization is 2 times 3 times 5, so 2 times 3 times 5. And for 50, the prime factorization is 2 times 5 to the second power. So when we look at the prime factors, we look at 2, and the greatest exponent is 2, so for the least common multiple, then it's a product of 2 squared, and so here's a 3 times 3, and then 5. 5, the greatest exponent is 5 squared, so 5 squared is 25 times 3 is 75, times 2 squared of 4 would be 300. So then the least common multiple is equal to 300 for the numbers 20, 30, and 50. So 300. Similarly, when we look at number 34, we have 14. Its prime factorization is 2 times 7. And 21, its prime factorization is equal to 3 times 7. And 40, its prime factorization is 2 to the third times 5. So therefore the least common multiple so for the factor of 2, the greatest exponent is 3, so the least common multiple would be 2 to the third, and there's only one 3 to the first power, and then 5, so there's only one 5 to the first power, and then there's 7. And so 3 times 5 is 15, times 7 is 105, 2 to the third is 8, and 8 times 105 would be 840. So 840 is the least common multiple. 840, which means it is the smallest number in which we can divide 14, 21, and 40. The other way of finding the least common multiple of a set of numbers is dividing by the prime factor method. So we write the numbers in a row, and then we divide the numbers by a common prime factor. Try 2 and then 3 and so on, and divide the quotients by a common prime factor. And no prime will divide all quotients, but a prime will divide some of them, divide where possible, and bring any non-divisible quotients down. We'll show you how that works. Continue until no prime will divide into any two quotients. And then the product of all prime divisors from steps 2 and 3, as well as all remaining quotients, is the least common multiple. So let's do some examples. Use a method of dividing by prime factors to find the least common multiple of each group of numbers. So number 35, we're talking about finding the least common multiple of 27 and 36. So we begin by writing 27 and 36 next to each other. And one prime factor, of course, is 3. So we divide 27 by 3, we get 9. And we divide 36 by 3, we get 12. So 3 is another prime factor. We divide 9 by 3, that would be 3. And 12 divided by 3 is 4. And there's no more common prime factor. So then the product of these numbers will be the LCM. So in other words, the LCM is equal to 3 times 3 times 3 times 4, which is equal to 108. So that's the least common multiple for these two numbers, 108. So for 14 and 63, we write the numbers next to each other, 14 and 63, and so 7 would be a common prime, so 14 divided by 7 is 2, and 63 divided by 7 is 9. Well, it's 9. And there's no more common prime factor for 2 and 9, so we cannot bring down anything. So in other words, the product of the LCM is the product of these three numbers. So the LCM is equal to 7 times 2 times 9, which is equal to 108. Correction, it's 126. So 126 is the least common multiple. And we do a similar calculation for the next exercise, number 37. So we write the numbers 63 and 99 next to each other. And the first common prime factor is 3. So we divide 63 by 3. That gives us 21. And when we divide 99 by 3, we get 33. And 3 is another common prime factor. And when we divide 21 by 3, we get 7. And when we divide 33 by 3, we get 11. And there are no common prime factors. So then the LCM would be the product of these four numbers. So the LCM is equal to 3 times 3 times 7 times 11. And that is equal to 693. So that's the LCM, 693. And when we look at number 38, we do the same thing. We write 154, 165, and 2,310. For the number 38, we write 154, 165, and 2,310. And then we find 11 is a common prime factor. And so we divide 11 into 154, that gives us 14. And 11 into 165 gives us 15. And 11 divided to 2,310 is 210. And now we can divide the prime factor of 7 into each of these numbers. Well, in the first and the last, so that gives us a 2, and we bring down the 15, and this gives us a 30. And now the common prime factor is 2, so we divide that 2 into the 2 gives us a 1. We bring down the 15, and 2 into 30 is equal to 15. And now we have 5 as a common factor here. So 5 doesn't go into 1, but break down the 1. 15 divided by 3 is 3, and 15 divided by 3 is 3. And so then we have 3 as a common factor for the last ones here. So we bring down the 1, and 3 divided by 3 is 1, and 3 divided by 3 is 1. So then the product of these numbers is the LCM, the least common multiple. So that is equal to LCM is equal to 11 times 7 times 2 times 5 times 3 times 1 times 1 times 1 is 1. And that is equal to 2,310. So that's the least common multiple for this set of three numbers, 2,310. Another way of finding the least common multiple is to use the following formula. The LCM is the product with the least m and n. So it's the greatest common factors of m and n. But that method only works when you have two numbers. It cannot be, you cannot use it for three numbers. So then for number 41, the least common multiple using the formula is equal to 18 times 60. That's our m and n. And the greatest common factor of m and n was equal to 6, so that equals then 180. So 180. Similarly, for number 42, the least common multiple for 77 and 82, so we take the product of 77 and 84, rather, divided by the greatest common factor of m and n. And the greatest common factor of 77 and 84 is 7. So we divide 7 to 77, that's 11. And 11 times 84 is 924. So that is the least common multiple for the number 77 and 84. So 924. So for number 43, so the least common multiple is equal to 36 times 90 divided by the greatest common factor of 36 and 90. So that would be equal to 180. And for number 44, the least common multiple is equal to 72 times 96 divided by 24, the greatest common factor of these two numbers, 24. and the product, that product is equal to 288. 288. And so this was 180 for number 43. In number 60, about sawing lumber, Terry has some pieces of 2x4 lumber. Some are 60 inches long and some are 72 inches long. All of them must be sawn into shorter pieces. If all sawn pieces must be the same length, what is the longest such piece so that no lumber is left over? So we are finding the greatest common factor of 60 and 72. So we can use the prime factorization method. And so for 60, that's equal to 2 to the second, 2 to the second times 3 times 5. And 70, the prime factorization is 2 to the third times 3 to the second power. So then the common factors are 2 and 3, and the smallest exponents are 2 and 1. So then the greatest common factor is equal to 2 squared times 3 to the first power times 3, or 12 inches. If she saws these 2x4s into 12-inch pieces, there won't be any number left over. In number 58, we have two bicycle racers, and they follow a circular track. If they start at the same place and travel in the same direction, and Thomas completes a revolution every 40 seconds, while Philippa takes 48 seconds to complete each revolution, how long will it take them before they can reach, or before they reach the starting point again simultaneously? So we are asked to find the least common multiple of the numbers 40 and 48. So if we use the prime factorization method, 40, the prime factorization is 2 to the third times 5, and 48, the prime factorization is 2 to the fourth times 3. Therefore, the least common multiple is equal to, we use the greatest exponent, 2 to the fourth, times 3, and then times 5, and that would be equal to 240 seconds, or 4 minutes. Or 4 minutes. And this concludes section 5.4.